Hi, I'm Ari Zitin, an analytical training consultant here at SAS, and today we'll be doing a tutorial on activating the model interpretability tools in SAS Viya's Model Studio. So the question is, what is model interpretability and why would you want to use it? So some of the questions that you might ask yourself when you're building models are questions like, did the model work? What are we going to do with the results of the model? Was the model fair? You can get some answers to these questions with the model interpretability tools. So did the model work? You can use the model interpretability tools to give you some intuition for how the model is thinking about your data, what kind of inputs it's using to predict the target, and what it's doing with those inputs. So it can give you a verification on you can sort of check your intuition, what you think the model ought to be doing or what kind of inputs it ought to be using versus what it's actually doing. Questions like, what can we do with a model? Some models are only useful if they're interpretable. For example, if you're building a model to try and change your business processes, you might want to know why the model is suggesting what it's suggesting so you can explain to business leadership why you need to make the changes you need to make. On the flip side, if you're building a model that's just trying to find customers who are most likely to respond to a mailing campaign, you might not care about model interpretability. So I always think about what you want to do with the model, whether the model's working. The other end, the other sort of side of model interpretability is the model fair and does it meet standards that regulators have assigned for you? So when you're giving people credit scores, they need to be able to find out what they did wrong or what they need to do to get a better credit score to try and get a better loan. And so then you have regulatory requirements based on how to explain your model to the customer and the regulators to make sure that you're doing it right. In terms of fairness, of course, there's also, is your model using protected classifications or characteristics about people to try and make predictions? Is your model discriminatory or biased? Model interpretability can help you answer these questions by telling you what the model is thinking. So in order to get into the details of what model interpretability really means, we'll look at some models and think about how to interpret these models. So we'll start out with a classic logistic or linear regression. We'll sort of think of logistic regression. So if we have logit, this is just sort of a formula. Logit of p hat equals beta 0 plus beta 1 x1 plus beta 2 x2. So this logit score, p hat is our probability. So we're trying to predict, probabilities based on our inputs. And the idea is that we can interpret this model because these coefficients, beta 1, beta 2, tell us how we change the logit score, which is essentially the log odds of the probability, as we change x1. So if I increase x1 by 1 unit, it increases the logit score, which is the log of the odds. So it would be log of p hat over 1 minus p hat. It changes the logit score by an amount beta 1. So what that's basically telling us is that we can interpret the logistic regression by using these estimates to tell us how our probability, so that's the predicted probability of whatever we're trying to predict in our machine learning algorithm, how the predicted probability changes as we change our inputs. So this is interpretable because it tells us what happens if I change this input. In the context, I always like to think of someone's applying for a loan and they're asking, why didn't I get the loan? And we could say, well, look, your X1 is the number of delinquent credit lines you have, and it was above a certain threshold, which means that your probability of defaulting on the loan was above a certain threshold, so we denied the loan to you. The next example I think about of an interpretable model, so the conclusion here, though, is basically that logistic regression is a fundamentally interpretable model. So the next model that we'd sort of think about as a fundamentally interpretable model are decision trees. So if we imagine we have some decision tree, here's the leaf, here's the root node, and then it splits. There we go. And it splits based on, let's say, x1 is less than 0.5, and this is yes, and this is no. And then we have over here, x2 is less than 0.6, and this is yes, and this is no. And let's say people who follow, and I'm not going to draw the whole decision tree, but let's say people who follow x1 is less than 0.5 and x2 is less than 0.6, we classify these as a 1, and we classify these people as a 0. And let's say this one is, 70% probability, and this one is 60% probability that we classify it as a 1. We can get an explanation because if we end up in this bin, and let's say we classified them as a 1, which let's pretend, again, we're imagining default data. So we're predicting that they're going to default on their loans. And when they ask us why, we can say, well, your value of x1 was below 0.5. Your value of x2 was below 0.6. And we found 60% of people who shared those characteristics defaulted on the loan. So you fall into that bin, and we predict you'll default on the loan. If you wanted to change it, we could try and adjust your values of x1 or x2, which could be things like delinquent credit lines. So once again, this decision tree is a fundamentally interpretable model because we can read off from this list of rules why we scored someone the way that we did. Now let's move on to think about some of our fundamentally uninterpretable models. So if we think about neural networks, the neural network forms an equation. So we have, I'll just draw a little neural network diagram here. Let's say x1 and x2, x1, x2. And let's say we have 3 hidden units. And x1 and x2 connect to all of those hidden units. And let's say we only have 1 hidden layer. The problem here is still that if we change the value of x1, it affects this hidden unit here, this hidden unit here, and this hidden unit here. And it depends, the way that it changes the outcome depends upon the instantaneous value of x2. Because each hidden unit has this formula, something like tanh of w0 plus w1 x1 plus w2 x2. And so what you'd see is that the output of this tanh right here depends upon the value of x2, not just how much we change x1. So what we see is that even though it looks like a formula like logistic regression, we cannot individually and independently isolate the effects of each individual variable. And so we can't really interpret how changing a variable is going to change the outcome. At the end of the day, the neural network is just a big formula, and we plug all your inputs into the formula, and it makes a prediction. And if you ask, well, what would happen to the prediction if I changed x1 by an amount 0.5? Well, the only way to know would be to change x1 by an amount 0.5 and plug it right back into the model, which really is an interpretation. We're just saying, well, the model said so because this is what the model says. So they're fundamentally uninterpretable models. The next one we think about is forest and gradient boosting. I'll just draw like a little diagram. The forest is really just a collection of decision trees. So I'm sort of drawing a bunch of different decision trees on here. They look kind of like stick people. Forest and gradient boosting both involve amalgamations of decision trees. So even though each tree has its own list of rules that we can interpret, when we average them, we can't really interpret that anymore because some combination of a list of rules doesn't really give you some summary list of rules. Rather, we're just averaging all the probabilities generated by the trees. So at the end of the day, none of these rules are the actual rule we'll use to score the model. It's some numerical average or amalgamation of them. And we can't really make an average explanation because all of a sudden, all of the variables end up being important in predicting the target because depending upon which tree we're looking at when we do the averaging, we'll essentially be looking at different variables or different pathways. So there's no one unique list of rules that we can use to predict or to explain why you predicted what you predict. So moving on, we'll now get into the software and the data that we're going to use. So we'll be using data from the Titanic. So people who survived when the Titanic sunk. We have information about essentially about historical information about the passengers, what cabin they were in, how old they were in, their gender. And we're going to use that to try and predict whether they survive or not when the Titanic crashes. So the first thing I'll do is go to the software. So I'll open up Google Chrome and go to SAS Viya. I will navigate to SAS Drive, which is sort of the homepage for SAS Viya. And I'll talk a little bit more about the data we're using once I load up the data in the software. From SAS Drive, I'll click the hamburger menu in the top left. It's also called the Show Applications menu, but sort of universal name, the hamburger menu with the 3 lines. I'll go to Build Models. This takes us to SAS Model Studio. From SAS Model Studio, I will create a new project. So I'll click New Project, and I'll call this Titanic Model Interpretability Demo. I'll use a blank template and select my data. This is going to be the Titanic data. So I'll go to Import and just import it locally from my local machine. Data D, Workshop, SAS, UA19. This data is available. There's a link to it below. So you can find this data yourself. I'll click Import Item to load it up into memory. It's a small data set, so it should be pretty quick. Oh, it's actually giving me an error that the table already exists. I'll just replace it for good measure. I probably didn't have to do this since the table was already in memory, but I'd loaded this up earlier today. I'll click OK. I'll go ahead and click Save. So this builds our project with the Titanic data, and it immediately starts by taking us into what I call the Data tab in Model Studio, which gives us some information about the data that we just loaded in. And I'll talk about some of the inputs as I go through getting rid of the ones that I don't want to use. So the first thing, we are doing predictive modeling. You must assign a variable with the role of target. We need a target. We want to predict whether people survived when the Titanic crashed and they fell into the freezing North Atlantic water. We'll click survived. I'll change the role from input to target. Now we want some inputs to try and predict the target. So I'll just sort by type. All these character variables, we can pretty much, I will sort by role because I care about whether they're inputs or not. The ID variables we can leave. For key ID, I'm going to change this from an ID to a key because we're going to use this as a key to reference individual rows in our data. So I'll click key under key ID. I also want to reject some variables. I'll select embarked and parch, and I'll scroll down, and boat's already rejected, and I will reject these two. So I'll switch it from role of input to the role of rejected. That leaves us with 5 input variables that we care about. So I'll resort this just so we can look at all 5 of them all together. We have sex, so that's male or female. We have age, which is a numeric variable about how old they are. We have fare, which is a numeric variable about how much they paid for their tickets. We have P class, which is a categorical variable. And I guess I should switch. Oh, and it knows the level is nominal, so it accepts that. So it's class 1 for first class cabins, class 2 for second class cabins, class 3 for third class cabins, the cheapest cabins. And then siblings and spouses at SP, which is the number of siblings and or spouses that you had on board. So the way I always interpret this is if you've got 1, it's probably a spouse. If you've got more than 1, I don't think very many people in the Titanic brought more than 1 spouse with them. So we've got our data prepared. And so we'll now go to the Pipelines tab. So I'll click Pipelines. And I'll start by just building a simple predictive modeling pipeline here. Right-click on Data, Add Child Node, Supervised Learning. I'll build a decision tree. I'll also right-click on Data, Add Child Node, Supervised Learning, Gradient Boosting. So I've got an interpretable model, the decision tree, and an uninterpretable model, the gradient boosting model. I'll click on the gradient boosting model, and we'll find something fairly exciting. Did you know we can turn on model interpretability with just 1 click? So we're just going to open the global interpretability, click PD plots to turn on the model interpretability. We actually have a few more clicks to get the rest of our model interpretability tools. So once we've clicked PD plots, I'll scroll down to local interpretability. I'll select ice plots. I'll turn on Lime. Incidentally, I'm going to explain what all of these things mean when we actually look at the results. But you'll notice you don't really have to know what they mean to just click them and turn them on. And I'll leave all these settings at the default and go ahead and run the pipeline. While it's running, we'll look at the results of the decision tree to see how we can interpret it. But we find that ultimately the gradient boosting model performs a little bit better. So it's a slightly better model, and we want to be able to use it, but we only can accept it if we kind of understand how the model is working and interpret it. So we've turned on some various model interpretability tools. We'll look through the results of the decision tree, and then I'll start talking about these individual model interpretability plots, and we can look at the results and really try and make our interpretations. I'll right-click on the decision tree, select results. When I interpret the decision trees, what I really like to look at is the decision tree diagram. So that's the tree diagram right here. I'll expand it to full screen and zoom in. So we see immediately there's a split based on sex. Males over here, females over here. We see that surviving is a 1 and dying is a 0. So we find that females are much more likely to survive the sinking of the Titanic than males. And if we follow the male pathway over on the left, we see that for males aged 5.25, so basically older than 5 years old, we find that approximately 82% of them died when the Titanic sunk. So this matches our intuition, which is if you sort of look up historically about the Titanic, there was this philosophy in the late 1800s and early 1900s. For ships, when ships sank, they saved the women and the children first. So this is indicating if you are not a woman and not a child, your chance of dying is much higher than everyone else on the boat. So we could continue to interpret the whole tree diagram. Instead of doing that, I'll go to the results from the gradient boosting node. And actually, I'll close the results of the decision tree node. We'll right-click on gradient boosting, select results. So we get some summary results of the gradient boosting model, which really tell us how well it did. Things like this error plot, which shows us the training data, the validation data, and the test data as essentially the average squared error of these data as a function of the number of trees. So we're seeing as we add more trees in our model, we get better performance. So the gradient boosting model does better than the individual decision tree, which is just a single tree over here. However, we no longer have the tree diagram. I could scroll through all these node results and search to my heart's content, and I won't find a tree diagram because there doesn't exist one. So now we have to go to the model interpretability results that was generated when I turned on all those model interpretability tools. So I'll click model interpretability, and we'll go to the partial dependence plot. So I'll start by looking at it, and I will give some explanations. On the right is a little summary description of what we're looking at in the plot. I find this is useful as a reminder, but sometimes when you're learning these things, this automatically generated text is a little too formal. So I'll give you sort of a description of how I think about the partial dependence plots, and then we'll talk about how we make them. So what we're looking at here is that on average over the whole data set, we predict for females, we get a 0.66% chance of survival. So that's 66% chance of survival. And for males, on average, we get a 21% chance of survival. For age, which is a continuous variable rather than a discrete variable, we get a continuous prediction for the different average predictions based on the age. So we're essentially we see that for people under the age of 15, we see they're much more likely to survive than people over the age of 15. And if you're over the age of 50, your chance of surviving in the cold North Atlantic water goes down quite a bit, which matches our intuition. They saved the children first, and people above a certain age simply don't have the capacity to swim in cold water for a very long time. So we get these results, and then the question is, how do we construct these results? What did we actually do to generate these? So I'll actually minimize the software real quick, just to do a little bit of a drawing to explain what we're doing. One sec, I'm a little tangled up right here. So when we build the partial dependence plots, we imagine we have the full data set. And let's say this is an input like age, and these are all the other inputs, sex, etc. And then here's going to be what we want to predict. So what we do is we take all of our original data set, so these are the original numbers, and then we plug in. So let's say we want to make a partial dependence plot, PD plot on age. So we plug in age equals 1 for every person. So we're imagining, let's say the Titanic, instead of being filled with adults, we sent a full Titanic of 1-year-olds, but they were all the same people. They had all the same characteristics, the same sex, the same class. They spent the same money on the fare. We predict for everyone 1 year old, what is their predicted probability for the target? We generate all these numbers, so that's on the predict column here, and then we average them. We average all of our predictions, and that becomes a point on our partial dependence plot. So I can imagine this is age, and this is, average target. And what we imagine is now we've got a value at age equals 1. So we have 1, and we plug in this average that we calculated up here. We now iterate this. So let me grab my eraser, erase these values. And now we switch age to 2. Inadvertently right-clicked, excuse me. And then we do another average prediction. And we plug in the result for age equals 2. We do this for all the different values of age. And now I'm going to go back to the software so we can actually look at a plot that wasn't drawn super haphazardly. Let me erase all of my results. So now if we look at the partial dependence plot, we see this is basically like a scatter plot for all these different values of age. And you can actually see they didn't do age. And so age equals 1, age equals 2, age equals 3. So we get all these average predictions for our target variable. What this is showing us is overall what the model is thinking about this variable. So we're washing out individual effects, but we get these averages that help us explain how changing age might change the target prediction. We can now look at the one for sex. This tells us women survive better than men. For age, it tells us young people survive better than older folks. All this matches that intuition where they save the women and children first. If we look at fare, we see people who paid more for their fare tended to survive a little bit better than people who paid lower for their fare. The way I always think about this is that the people who paid more were in the first class cabins, so they were on top of the boat. When it went to sink, they got out much faster than the people who were at the bottom. We see this straight line here because there was probably only one or two people who paid more than $100 for their fare. This is like the oil magnates who had the executive suite on the top of the ship. And so our model doesn't really know how to predict for those people because it only had one example. So it makes basically a constant prediction for higher fares. We can look at P class, and this matches our intuition. First class has the highest percentage of survival. Second class is lower. Third class is lowest. And then I find siblings and spouses hard to interpret. If you had more than 3 siblings or spouses, your chance was slightly lower. When I look at this plot, it tells me this variable is not very important. It doesn't have as big of an effect on the target prediction as the other variables. So that's partial dependence plots. And these partial dependence plots can be useful, but they only show us average information. So it's averaged over the entire data set. In order to drill down into a little bit more local information, we need some local interpretability tools. So the next plot we'll be talking about are individual conditional expectation plots. These individual conditional expectation plots do something very similar to the partial dependence plots, but they're clustered in groups based on similarity. So I'll scroll down in the results here, all the way down to individual conditional expectation. We now have 2 clusters, cluster ID 1 and cluster ID 2. We generated these clusters by just doing k-means clustering on the original input data. So we're clustering based on similarity of all the other input variables. And here we're looking at essentially what would be a partial dependence plot, but it's now averaged within the clusters. So the idea is for cluster 1, we look at average prediction if everyone in cluster 1 was female, and we do the averaging to average for everyone within cluster 1. And then we look at what if everyone in cluster 1 was male, and we average within cluster 1. We do the same thing for cluster 2. So in many ways, we're doing the same thing as partial dependence, but instead of averaging over the entire data set, we're just averaging over a subset of the data set. Now, abstractly, you could imagine doing an individual conditional expectation plot not using clusters, but using each individual observation. And so in this plot, it's a little bit easier in the numeric plots. If we look at age, instead of seeing 2 lines, one for each cluster, we'd see 1,309 lines, one for each person on the Titanic. Now, of course, that's not really an interpretable plot, so we do it in clusters to get sort of a higher resolution view. Or I guess a lower resolution view would be the best way to put it, a higher perspective rather than a zoomed in on each individual observation. At the end of this, I'll give a demo of doing it for each individual observation, but we only look at one line at a time. So it's sort of how you'd explain a single person's prediction. The important part for individual conditional expectation plots is that we can now see differences between the clusters. So what we're seeing here is that cluster 2 has a lower predicted probability of survival in general than cluster 1, right? For females, it's 0.5 instead of 0.89. For males, it's 0.2 instead of 0.43. However, the relationship between the input, the relationship between sex and your predicted probability of survival is the same for each cluster. For cluster 1 and cluster 2, if you're a woman, you're more likely to survive than if you're a man. So you see the same relationship, which means that basically we're looking at the same results we saw in the partial dependence plot. It's just split out into 2 clusters. The story is different for age. When we looked at the partial dependence plot for age, we saw this curve, basically, the gold curve, which corresponds to cluster 2. We didn't see any curves that look like this one for cluster 1 because it got washed out when we did the averaging. What this is suggesting is there's one group of customers, this is just my guess, but these are customers who probably paid less for their tickets and were in 3rd class, where if you were under the age of 15, you were much more likely to survive. However, there was another cluster of customers where pretty much everyone was likely to survive. I think of these as probably our wealthy customers who are in the 1st class cabins. So for these people, in cluster 1, it seems like age really doesn't have very much of an effect on their predicted probability of survival. But for cluster 2, age really does have an effect. This is the kind of information that we wouldn't be able to see in the partial dependence plot, and we'd have to use this individual conditional expectation plot in order to reveal it. Basically, cluster 1 was smaller than cluster 2, so when we did the averaging, the relationships get washed out. I like to look to see if I see anything else in the rest of these plots. So if we go to fair, we see even though cluster 2 has a much lower % chance of survival than cluster 1, the relationship between fair and the predicted probability is basically the same. It's sort of the same shape curve. I mean, there's some slight differences here, but it sort of increases a little bit and then levels off. So we see, really for fair, we see the same relationship as we saw on the partial dependence plot. For P class, again, it matches first class, second class, third class. It does look like we have two different clusters. Cluster 1, first and second class are pretty similar. And in cluster 2, second and third class are pretty similar. So it seems like maybe these clusters were based on gender or where they were in the boat. We'd actually have to drill down into these clusters. And the software allows you to generate score code from the clusters. So you can then assign the original data into the clusters and see where they are, basically see who's in what cluster. Now, just like in the partial dependence plot, we don't really see any particularly interesting relationships in siblings and spouses. We see that cluster 2, again, has a much lower chance of survival than cluster 1, but we're really interested in how siblings and spouses affect your % chance of survival, which we don't really see any interesting relationships. I'll close the results from the individual conditional expectation plots. Our next model interpretability result is local interpretable model agnostic explanations. These local interpretable model agnostic explanations, or LIME plots, or LIME models, I guess, because the E is for explanation in LIME, is basically doing a local linear fit to your data to try and explain your model using a linear regression locally. So we're taking an unexplainable model, like a neural network or a gradient boosting model, and we are explaining it locally using this, essentially a model that is only fit locally to the data. So I will start drawing a little bit of a picture while I explain the steps here. One moment. So basically what we do is we fit an uninterpretable model, and I'm going to sort of draw the decision boundary for an uninterpretable model. Let's assume we have two axes. This is something like age. By the way, I'm just making up this drawing, so this isn't from the data. This is just an illustrative drawing. Let's say we have two axes, age and fair, and our original model, so this is our gradient boosting model, the uninterpretable model, generates this decision boundary. So points in the blue region, it classifies as people who will survive, and points in what I'm going to draw on as the red region correspond to people that the model predicts will die. So these are the predictions of our uninterpretable model. Now, of course, if we could draw such a nice picture like this really is an interpretation of the model, but we're imagining normally it's going to be in higher dimensions. Right now we have age and fair. In our real data, we actually have 5 dimensions. I think you probably know why I have chosen not to draw a 5-dimensional decision boundary here, because I can't. It's always harder to visualize in higher than 2 dimensions. But so we have this uninterpretable model here. And now let's say we want to explain a point. Let me grab my black cursor again. Let's say we want to explain a point that is right here. So we want to ask, why did this point get classified blue? Why did this person survive as opposed to die? Well, the first thing we do to generate the LIME explanations, I guess I should call them. I always want to say something after LIME, but the explanation is built in. So we sample data points in this space. So we choose basically like values of age and fair, such that we're just sampling points. So let's say we select a point here, we select a point here, we select a point here, and select a point over here, select a point over here. So we select some points in our space, and we're going to use these points to fit a local linear model, and maybe a few more points nearby. The important part about selecting these points, which we're going to call perturbed samples, is that the points we select near our point of interest, which I should probably put with a big X here, are going to be weighted more heavily. So these points that are close to our point of interest are going to be bigger, and these points further away are going to be smaller. And so that's maybe a point here is super small. So we're basically saying we're selecting points, and we're going to use those points to fit a local model. The points that are closer to our observation of interest, which is really the person we want to explain why they lived or died, are going to be bigger because they're going to be weighted more in our local linear model. Once we've generated those points, we're going to score them using the original uninterpretable model. So this point, it's in the blue region, so it'd be blue. This one would be blue in the blue region. This point's going to be red in the red region. This is a bigger red point in the red region, sort of medium size because it's a little bit further. This is a big point in the blue region, maybe a slightly smaller point in the blue region, and maybe a larger point in the blue region. And then once we've scored those points using the uninterpretable model, we use those samples to generate a local linear regression to try and explain the boundary here. And so this is the geometric intuition that I think is really valuable here, is that basically we're doing a linear approximation to this curved blue line here is a curved decision boundary that we can't really explain, and we're just going to generate a linear approximation to it. One thing I like to highlight about this linear approximation is that it's obviously only valid around this point. So it's only valid in this region. You could see this linear approximation doesn't even come close to approximating the decision boundary over here, but it does a good job right here. This linear approximation then has coefficients that we can use to explain why this point, this big black X, gets scored on this side of the blue, the boundary, as opposed to over here. One thing I like to highlight that really helps me build intuition is if our point, let's say our point of interest was actually over here, then our local linear model would be local to this region, and we would expect maybe something like this. The intuition that and that of course isn't a line, sorry, I should have drawn that as let's pretend this is a straight line. I am not a ruler. And the idea here, and this sort of comes from math, if you're familiar with Taylor expansions or calculus, basically if you zoom in close enough on a curve, it looks like a straight line. And so if we zoom in close enough to these points, we can generate a linear model that approximates the nonlinear decision boundary that we have. So that was a lot. We'll go back into the software to look at the results of these linear models and see how we can interpret them. I will go ahead and clear that so you can see what's underneath. So we start out, here is just a summary of the local model. The first thing you notice is that there's the words cluster centroid 1. So instead of fitting a local model to each point in our data, so that would be 1,309 points, so 1,309 local models, we fit them to the clusters. So just like when we did ICE, we did the clustering to separate out so that we wouldn't have to look at each individual observation. In this case, we built clusters, and the cluster centroids serve as the point around which we're generating the local model. So that big black X that I showed, that could have been a person that we're trying to explain. In this case, it's just going to be the center of a cluster. So we fit two different local models, one for cluster centroid 1 and one for cluster centroid 2. And you can see we have estimates, parameter estimates, for each of these cluster centroids. And this is a local linear model. We can evaluate how well it did. I'll close those results so we can just look at a plot. So what this is saying is that in cluster centroid 1, most of the observations had a sex of female, and that being female improved their chances of survival. In cluster 1, most of our people had a class of 1, so they were in first class cabins, and that also improves their percent chance of survival, slightly less than being female. And so again, that matches they saved the women and the children first. However, as we normally expect, people in first class cabins probably get better service and are closer to the exit. And then we see that siblings and spouses is a lot less important in predicting the target. And so we see that it seems like being female and in first class is really what caused most of our observations in cluster centroid 1 to be predicted to survive. If we go to cluster centroid 2, we can see that their gender being male decreases their percent chance of survival, and their class being third class also decreases their percent chance of survival. Once again, having 0 siblings and spouses, which most of our passengers on the Titanic did, sort of slightly improves their chance of survival, but does not offset being in third class and male. We'll close these results and look at the same thing for interval variables. We see age is a negative predictor for the target, so that means the older you are, the less likely you are to survive. And fare is a positive predictor, so the more you spend, the more likely you are to survive. This tells us that age is a lot more important in predicting your survival than fare. We look at cluster centroid 2, we see the same relationship. That's really the relationship we found in the partial dependence plot. Age is a negative predictor. Fair is a positive predictor for your chance of survival. I'll close these results. We can also look at local fit statistics to see how well the model did. Remember, the local model isn't actually trying to predict who lived and who survived. It's trying to predict who was predicted by the gradient boosting model to live or survive. Basically, instead of trying to predict the true target, it's trying to mimic the predictions of the uninterpretable nonlinear model, the gradient boosting model that we originally fit. I'll go ahead and close these results and move on to talking about individual observations. So we did the ICE plots, individual conditional expectation, and the LIME, the local interpretable model agnostic explanations. We did these on clusters. Now we can do it on an individual observation. So I'll scroll down to the bottom on the gradient boosting. I'll open up local interpretability. I'll scroll down all the way to the bottom, and I'll open general ICE LIME options. Scroll down again. Type of instances to explain, I will switch it from cluster centroids to individual observation. It asks for a number here. It's going to be the key ID. If you remember back when I set the variables, I set a variable to be a key. That was key ID. I'll just enter 1. This is the first observation in our data set. I can open up our data and look at it. I happen to remember this is, I believe, Miss Elizabeth Allen, and she was a 29-year-old woman who did end up surviving. And we're going to explain why the model predicted what it predicted for her. So once I've made this change, I'll rerun the pipeline. And it'll generate individual conditional expectations and local interpretable model agnostic explanations for just this one observation. So if we think back to that picture that I drew about the line plot, basically instead of this X being a cluster center, the X is now Miss Allen. So it's going to be her age and her fair and her class, all that information. So I'll right click on gradient boosting. I'll select results. I'll go to model interpretability. The results of the model shouldn't change. All that's changed is the interpretable results. So now I'll full screen the individual conditional expectation. We'll see since she was female, we predicted her probability of survival would be 0.86, so 86%. If she were male, her probability of survival would be about 40%. Her age, I happen to remember from the data, was about 29, so somewhere right in here. Here's our prediction for her probability of survival at different ages. And so this gives us a somewhat unexpected result, which is that if she were younger, we actually predict she'd be less likely to survive. And if she were way older, we also predict she'd be less likely to survive. Remember, this has no averaging now. So this is just the predictions if we were to change the value of, we keep all of her characteristics the same. So she was in first class and she was a woman. And we evaluate what the model thinks she would do if we changed her age. One thing to note is that since she stays a woman the whole time, her predicted probability of survival is pretty high. So it's going to be above 0.75 no matter what. We can look at other things like fair. We see sort of the same relationship. P class. We see if she was in first or second class, she gets the same probability. But if she got dropped to third class, her probability of survival would go down. This sort of matches our intuition, which is that women in first and second class were able to survive with a pretty high rate. Women in third class didn't survive quite as well. And of course, men in third class survived the least well. In general, folks in third class did not make it as much as folks in first and second class. I'll close the results and I'll look at the local model. So now this local model is local to her observation. So it's valid somewhere near her. And so really this is an explanation for why we classified Miss Allen as a survivor as opposed to someone who died. If we look at sex, she was female, which improves her chance of survival dramatically. She was in first class, which also improves her chance of survival. And the same relationship we saw with siblings and spouses, where it doesn't have a huge impact. We also look at the local explanation for interval variables. We see her age actually decreased her chance of survival, according to the local model, which runs a little contrary to what we saw in the individual conditional expectation. But the local explanation is probably a more valid explanation because it fits this local linear model. And then we see her fare. She spent $211 on her ticket, so she got a pretty expensive ticket, which is probably why she was most likely to survive, a wealthy aristocrat. I'll close these results. we could go through this for other observations. If really the way I think about using this tool is if someone wants to know why they got scored the way that they got in your model, you could pull out a local observation for that particular individual or for their observation in the data, and you could build this local model around them to try and explain why they got classified the way that they did. So I'll close these results. At the end of the day, we now have our gradient boosting model, which we can interpret using those model interpretability results. Now, of course, the model interpretability results are only meaningful if you can interpret the inputs. And that's sort of a big message of this discussion, is that no matter what you're doing in order to interpret your model, you need to understand what your inputs are. And you're really trying to use the model interpretability results to come up with an explanation or a story for why your predictions are the way that they are based on the inputs. I hope you learned a lot about model interpretability and some of the model interpretability tools we have in SAS Viya. Click to subscribe to the SAS users channel. Click here to answer some questions to help us make better videos. And then down here are some links both to the data as well as on some papers that go into more detail or give you a nice refresher of what we talked about.